So thanks to the organizers for inviting me and for organizing this conference through all the problems. So my talk focuses on what we have been learning about galaxy evolution from spectroscopic surveys of galaxy clusters at redshift less than 1. And by clusters, I really mean halos more massive than 10 to the 14, 10 to the 13.5 solar masses or so. And I would like to start by mentioning at least some of the large spectroscopic surveys that have been dedicated to clusters in particular. So both multi-object surveys, MOS, and integral field surveys. And the first ones, the first lists are multi-cluster large surveys, but of course there are innumerable spectroscopic campaigns of individual clusters, like spectroscopic campaigns of the nearby clusters, Coma, Virgo, Fornax, both MOS, and now there is Fornax 3D. And dedicated cluster surveys have given an enormous contribution to this field of research, but a very important contribution also has come from the so-called general spectroscopic surveys, of course, like Sloan or Gamma on the MOS side, and SEMI or MANGA on the IFU side. And these two are really complementary. The cluster dedicating and large spectroscopic surveys are really complementary to each other. And usually what you can do with one, you can't do with the other, and vice versa. And there are several talks. I hope you have heard the talks by Anna Galassi on Monday, and there are other talks regarding the general spectroscopic surveys. I will focus on the cluster dedicated surveys. So I'm going to argue that almost all the major results on galaxy evolution in clusters came thanks to spectroscopy, but there are some important and notable exceptions that I must mention, and there are a couple of them on this slide. So on the left, you have the morphology density relation, which is the dependence of the morphological fraction, so the fraction of elliptical, lenticulars, and spirals on the local galaxy density, number density, so number of neighbors per megaparsec square in this case. On the right, you see another non-spectroscopic result, which is the evolution of spirals into zeros in clusters. There is a large fraction of spiral galaxies evolving to zeros from redshift 1 to 0 in clusters. So just one note of caution before I start. So please keep in mind that talking about clusters and talking about density are two very different things. This is shown in a plot here I picked up. These are cosmological simulations. So if you focus on the bottom right, you see the distribution of 3D local densities. So these are simulations, so we know the distance, the physical distance in megaparsec cube from one galaxy to the other. And as you can see, the distribution of galaxy number densities in the virialized regions of halos does not depend on the halo mass, at least over 2 orders of magnitude in halo mass. So the intuitive belief that the most massive clusters are the densest environments is actually incorrect, unless you use a large number of neighbors. And also, one needs to be careful when making statements about how galaxy properties depend on environment, because some properties depend more on local density, some others more on the global environment, so being in a cluster versus the field or as a function of the halo mass. I will show you a couple of examples of these, and here I mentioned another one from Ellison that is concerns the gas metallicity, which is a subject I will not have time to touch, unfortunately. So some fun facts about clusters, why it's important. Well, in clusters, we can study both the so-called environmental effects like round pressure stripping, strangulation, harassment, and also all the rest. So there has been a lot of emphasis on environmental effects, but actually clusters can be used to study galaxy evolution in general. The other good reason is that in many ways, clusters can be thought as cosmic accelerators, so accelerators of galaxy evolution. They are the Ferrari of the universe. They start very fast. They go from 0 to 300 kilometers per hour in a few seconds, and they leave everybody else behind. And I'll show you what I mean by this in a moment. Of course, clusters are also the sites of super quenching because all the quenching processes are efficient, and I will discuss this as well, of course. So I will start from what is maybe, I don't want to say controversial, but it's maybe one of the most confusing aspects of galaxy evolution, which is the stellar mass assembly. So it's still a matter of debate whether the shape of the stellar mass function changes from clusters to field. And when I talk about stellar mass function, I am excluding the brightest cluster galaxy, which is a very special beast. Okay. Now, to make a long story short, I give you my personal bottom line for this. I think that it's pretty clear that the shape of the stellar mass function above log stellar mass 10 to the 10.2 or so does not change significantly between clusters and field, both at intermediate and low redshift. While if you go to lower masses, galaxy masses, it does. Now, this is surprising in many ways. First of all, because we know that the star formation histories of galaxies, also massive galaxies, are different in clusters and field at a given mass, as I'll show you in the next slide. And also, it is well established that the stellar mass function depends on the local density, also at the high mass end. Anyway, maybe we need to go to higher redshift, and here you see on the right redshift 1, 1.4, to start to see significant differences in the total stellar mass function, clusters versus field. Of course, separately, the quiescent galaxies and the star-forming galaxies, they are identical. They have identical stellar mass functions in clusters and field, but the total one starts to change. Okay, so I was talking about star formation history. And again, I'm going to give you the bottom line because this is in 20 minutes, it's really a long story. So it's well known that the average star formation history, so I'm talking star formation history, not star formation rate, the history, that the star formation rate as a function of time changes with galaxy mass. But it's also, I think, established that at a given mass, the star formation history changes from clusters to the field. And I'm not now at this point referring only to quenching. Even if you take only star-forming galaxies, galaxies that are still forming stars, you see this effect, and you see it in this plot here. This is star formation histories from full spectral fitting. So this is the average star formation rate as a function of redshift sorry, I pushed it too hard. For galaxies of different stellar mass beings, the colors, in cluster to the right and field to the left. So pick one color, the color you prefer, and you see that in clusters, the decline with time of the star formation rate is steeper, even if you just look at star-forming galaxies. So on the right, you have the Ferraris, as I was saying before. So the decline of the cosmic star formation rate density on a cosmic scale is known that is due to a combination of two effects: the quenching of a fraction of galaxies and the decline with time of the star formation rate of those galaxies that have not stopped forming stars, like star-forming ones. And between redshift 1.5 and 0, in the general field, the relative contribution of quenching and decline of star-forming galaxies is about 50-50%, while in clusters, galaxies in clusters today, the contribution is 75 versus 25%. So most of the decline of star formation is due to the quenching. So quenching, there are two aspects I want to highlight here. First, that clusters of galaxies possess a significant population of slowly quenching galaxies. And by slowly quenching, I mean on timescales longer than 1 gigayear. Again, there are many works. I have to pick one. In this case, I've picked the one from Chris Haynes. So this is the plot of the specific star formation rate. And here you have on top of the galaxy stellar mass, and here only star-forming galaxies. And you see that the cluster galaxies are below, have lower specific star formation rate than the field galaxy. So this has been shown in many works. The star formation rate mass relation in clusters is different from the one in the field, due to a population of star-forming outliers that lie below the star formation rate main sequence. And this is true both at intermediate and a low redshift. Intermediate, I mean the one I'm talking about, up to redshift 1, let's say. Maybe this is not true anymore at redshift 1.6. Maybe our chair could mention this more. The population of outliers in this diagram varies also with the host halo mass, also in the group regime, as gamma has shown, for example. So there is a population of slowly quenching galaxies, but this result seems in contrast with some of the Sloan results. For example, the Peng et al. Shown here, the star formation rate mass relation. Here the conclusions were, for example, that the star formation rate mass relation did not depend on environment. I don't have time to discuss all the reasons, but this is local density. These are 2 local density means, okay? So remember that in clusters, we do see a different star formation rate mass relation. But clusters also host a large population of fast quenching galaxies, and the most evident and robust examples of galaxies that have been recently quenched are the so-called K+A spectra, also known as E+A spectra or postharvest spectra. I don't like the name postharvest because this seems to imply that there was a burst before the truncation of the star formation, which is not always true. So I will use K+A, but I've heard many people use the word postharvest in this meeting. So we are really talking about the same guys, which are galaxies with no emission line in the spectrum. Here I'm taking pure K+A, but strong Balmer-Lime absorption. This combination of spectral features can only be obtained if the star formation was shut off at some time during the last gigayear, but the quenching time scale, so the time it took to go from normal star formation to 0 was short, was of the order of 10 to the 8 years, order of magnitude. Now, K+A spectra are proportionally much more common in clusters than in the field at all redshifts, and this is shown in the 3 plots here, going from the left to the right, higher to lower redshifts, and all these plots show the fraction of K+As of post-harvest spectra as a function of halo mass or something that goes with the halo mass anyway, okay? So the fraction is very high, the clusters have the highest fraction of K+As. It's also clear, I think, that the K+A phenomenon is related to run pressure stripping in clusters, at least at intermediate and low redshift, the ones I'm speaking about, while in the field it is often related to mergers, at least at low redshift. So it's important to keep in mind that different processes can give origin to similar spectra, so the spectra doesn't tell us what was the origin of it. Just to mention that obviously, as it was predicted and now observed, if you look at high redshift galaxies, massive quiescent high redshift galaxies, redshift 3 or above, they have post-harvest spectra. By definition, they had to be, because they just stopped forming stars and they had a major star formation episode, and they didn't have much time to stop star formation. Now, with the integral field studies, we now see the formation of K+A galaxies while it happens. Okay, so let me, here in this case, I'm talking about really run pressure stripping, which is very efficient in clusters. And I'm talking about galaxies that are recognizable to be run pressure stripping because they have some tail at some wavelength, okay. Of course, not all run pressure strip galaxies have these kind of tails, but bear with me. This is, for example, one galaxy. This is the Muse white light. These are the stars. And this is the corresponding H-alpha ionized Muse emission. Okay, so you can clearly see that the gas is being removed by the run pressure. Okay. Actually, you could already see the debris on this side because in the stripped gas there are stars that are formed, but I don't have time to show you this now. So if you look at this type of galaxies that still have ongoing star formation and a lot of gas, but the gas is being stripped, if you look at the external regions of the disk, at the borders of the disk, they have locally post-harvest signatures, okay? Because the star formation has been quenched fast in those regions. In the GASP project, which is the one I'm showing here, we also have purely post-harvest galaxies, so with no ionized gas at all, devoid of any gas, and they are spirals, of course. And we clearly see when we look at the stellar population properties, we see how the quenching proceeded outside in. So the quenching first happened in the outskirts because run pressure works from the outskirts inwards. And so the last star formation will be in the center, of course. Now, so quenching timescales, I've been talking about slowly quenching and fast quenching galaxies in clusters. Are they necessarily due to different mechanisms? And do they really imply, for example, that there is a slow plus fast quenching mechanism? I would say not necessarily. And this is really, we have to switch our brains from the integrated view to the spatially resolved view of things. And this is the previous slide I showed you. If you have a galaxy where you start to strip the gas from the outskirts, locally at each region, it will be a post-harvest spectrum. But it will take a while to strip away all the gas, simply because it takes a while as the galaxy infalls in the clusters and orbits, goes closer to the center, orbits around the center. It will take a longer time to strip it all. So overall, it's a longer process, but locally in the galaxy, it's a fast process, and it depends how you look at the galaxy. Interesting to see that, is there any overlap between the K+A galaxies, the outliers in the star formation rate mass relation, and those galaxies with the tails that I show you, that I recall ground pressure strip galaxies? There is zero overlap between this population, because by selection, K+A galaxies are non-star forming, while the round pressure strip galaxies sit on or above the star formation rate mass relation. This is shown here in coma on the right, in the Gasp sample on the left. There is a small but significant excess of star formation. So when they get stripped in the beginning, they have a small announcement of star formation. On the other hand, the star formation rate mass outliers, that are the guys down here in the star formation rate mass diagram, of course, by definition, are not above the sequence. So there is absolutely no overlap between these three populations. Now, I started talking about morphologies, and so I want a little bit to close the circle here and to show you that there is a correspondence between the quenching of the star formation and the morphological evolution. And this is one way to look at it. So the points are, each point is a cluster, and the red points are clustered redshift 0.6, and the black points are clustered redshift 0. And these points are the evolution, show the evolution of the spiral S0, elliptical, and early type fractions from redshift 0.6 to redshift 0. Okay, so you see that actually most of the evolution has not occurred at the highest mass end, but in the intermediate mass clusters. Anyway, the point I want to make here is that the light blue lines show you the star forming fraction. So the morphological evolution and the evolution in the star forming fraction are really parallel. Okay, this is not to say that on a galaxy by galaxy basis this happens, because clusters have a lot of passive spirals. So the morphological the morphological transformation takes longer than the star formation transformation. Okay, but overall, statistically, we are looking at one effect, not at two different effects. Okay, in order to do the review, I could not speak about I said almost nothing about the project I've been working on for the last 5 years, which is GASP. GASP, let me just say a few words at the end. So GASP started with the MUSE ESO-Large program, and then it had several multi-wavelengths follow-up. And the goal of this project is to study where, how, and why is the gas removed from the galaxies, and what is the effect on the galaxy's star formation history. The sample is quite small, it's only 114 galaxies, a low redshift. The mass range is large, 10 to the 9, 10 to the 11.5, but they are in different environments, in clusters, in groups, in filaments, and isolated. And I want to point out, especially to Daniel, I don't know if he is online, because he was talking about this the first day, that in GASP, we have a larger sky coverage because they are redshift 0.04, 0.07. With one muse or two muse pointings, we go out to on average 7 effective radii. So we can really study the outskirts, and actually we want to study the tails, so we really go out. But still, we maintain a good spatial resolution of about 1 kiloparsec, which is the same. Now, these galaxies have different types of stripping stages. So some of them are selected to have a strong unilateral debris, and some of them are at the beginning of these tails. Some of them have huge tails. Some of them are advanced in the stripping process. Some others are what we call the contour samples, and they don't have...
Time's up. Officially.
Yeah. I'm finished.
Time to start the Q&A.
Just the one slide. I thought you were giving me 5 minutes, but just the very last slide.
I gave a 5-minute warning just for, you know, raising my hand. I guess I have to give
okay. I see you
one.
walking around. Yeah. Okay. I conclude that this is the final one. So the key is the relation star formation in gas, and of course, the IFU data can tell us almost everything about ionized gas and stars. And going from Mars to IFU really is going from a description of the populations to understanding the physics at work. Now, in classes run pressure stripping today, a low redshift is the king. But if you want to see how Muse data can also help to understand other mechanisms, to identify and understand other mechanisms such as strangulation, accretion, cosmic wave enhancement, and stripping, go to see the results from Vulcani on the non-clusters galaxies. And here I just listed the few extra talks and posters that are at this conference. So you can see, you've already heard the Belaus yesterday. There is a pre-recorded talk by Mingozzi on the link between AGN and run pressure stripping outflows. And so you can look at the different posters. If you want to hear about gas metallicities, ask me during the questions because there was really no time. Thank you very much.